Welcome to my presentation about nonlinear ensemble transport smoothing. My name is Max Ramgraber, and this is joint work done in collaboration with my co-authors Ricardo Baptista, Dennis McLaughlin, and Yusuf Masouk. I originally presented this work at the International Symposium for Data Assimilation 2022 in Fort Collins, but since the conference was entirely in person, the talks weren't recorded. I'm hence re-recording it for posterity. So to introduce the method, perhaps it's good to start with a small reminder of what smoothers are. Basically, smoothers are specialized Bayesian inference algorithms which seek to estimate a posterior of a sequence of states given a sequence of observations. And most smoothers tend to do so sequentially, where the starting point is a smoothing posterior at an earlier time step, which is then augmented with a forecast to a new time step, where we sample new observation predictions, and then form a joint distribution of all states so far, the latest observation predictions, conditioned on the data up to the penultimate time step. And using Bayes' theorem, we can then condition this joint distribution on the next set of observations in the sequence, which gives us a posterior at the new time step and thus closes the recursion, setting us up for the next step in the loop. Now this down here is a fundamental update equation in sequential smoothing. The problem, of course, is that outside of a few special cases, we will never be able to solve this equation in closed form, this conditioning operation. So in practice, we need some kind of ensemble-based method to make it happen. And in the wider smoothing literature, there's two prevailing methods to do so. The first one is based on linear Gaussian assumptions and is exploited, for example, by the ensemble Kalman smoother, in which a prior ensemble is linearly transformed into a posterior ensemble, which has the advantage that it's really sample efficient, but the drawback is that its update is fundamentally linear, and thus only exact if all distributions involved are Gaussian, which is rarely the case in practice. Alternatively, we could choose an update strategy based on importance sampling, which is done, for example, by various flavors of particle smoothers, in which a prior ensemble isn't transformed, but instead the retrieval weights are changed, which has the advantage that it can implement arbitrarily complex and nonlinear updates, but the drawback is that it's very sample inefficient, often collapsing after a few of these operations in sequence. So these two methods in practice effectively occupy diametrically opposed ends on a line of computational efficiency versus complexity of the update, which is a problem in systems which are at once nonlinear and computationally expensive. The nonlinearity leads to non-Gaussian distributions for which the methods on the left are ill-suited, and the fact that they're computationally expensive leads to the fact that we cannot afford the ensemble sizes required by importance sampling methods. So in search of a free lunch, or at least a compromise solution, in this talk I want to advocate for transport methods as a potential third option. If you've never heard of transport methods, here's a very brief introduction. Fundamentally, transport methods seek a monotone and thus invertible function S, which takes us from a complicated target distribution pi, which you might only know through samples, to a much simpler reference distribution eta, often a standard Gaussian. In practice, this looks a little bit like this, where we have samples from a complicated target, and we want to find a function which transforms these samples into samples from a standard Gaussian. And because the map is monotone, we can also invert it and apply it backwards, converting samples from a standard Gaussian into samples from a target distribution. At its heart, transfer methods are based on the change of variables formula, which allows us to relate a random variable x associated with a target to a random variable c associated with a reference through this map. And we find a specific map which connects the two by minimizing the Kullback-Leibler divergence between the target, which we know through samples, and the pullback of a reference, which is the approximation to the target we get by applying the inverse map to a reference distribution. Now in practice, a lot of different kinds of functions could be used to implement this map, but we specifically care about triangular transit maps, which look a little bit like this, where the full map comprises of a number of map components, where the first map component depends only on the first entry of a target vector, the second map components depend only on the first two entries of a target vector, and so on, until the last map component depends on the full target vector. And this structure has a number of really interesting properties which don't fit into this talk, but the most important one we care about is that this kind of triangular map factorizes the target distribution, which allows us to sample conditionals of the target distribution. And this is a really useful operation in Bayesian inference. And to gain an understanding for why, let's take a look at a visual example. Consider that you want to map back from a standard Gaussian reference to the target distribution. This means we have to apply the inverse map, and to apply it, we have to invert all of its map components in sequence, starting by inverting the first map component on the top, which transforms the x1 marginal here on the horizontal axis into a marginal from the target distribution. This then gives us samples from the intermediate distribution, which is some marginals from the target and some marginals from the reference. And this serves as input for the second map component's inversion, converting the second marginal here on the vertical axis and thus yielding samples from the target distribution. Now the key thing about this process is that the inversion of a second map component depends on the outcome of the first. And this is a dependence that we can exploit to sample conditionals. Consider, for example, that we just skip past the first inversion step and replace its corresponding output x1 with a manipulated value x1 star that we have provided. If we then apply the second map component, pretending that nothing is out of order, then we of course no longer draw samples from the target distribution, but from a conditional of the target distribution, conditioned on these values we have provided. And to understand why this is useful for Bayesian inference, let us recall that all that Bayes' theorem does at the end of the day is just building joint distributions, then conditioning them. And if we can realize this with transfer methods, we're a large step closer to finding a general ensemble-based method to realize Bayes' theorem. Specifically in smoothing, we remember that the operation we care about is we want to condition the joint distribution of all states so far and the latest observation predictions on the next set of observations in the sequence, which is exactly this operation in the bottom right, just in higher dimensions. Now, if you want to use this operation, this conditioning trick, then there are a few things we have to watch out for in the construction of our map. First and foremost, to use this conditioning trick, we must skip past the entries that we want to condition on. So the values we want to condition on must occupy the uppermost entries of a transfer map. But this leaves us with a lot of freedom on how we arrange the remaining blocks for the states from x1 to xt. And as it turns out, depending on which kind of ordering we choose, we retrieve different existing smoothing algorithms. For instance, if we choose a forward in time ordering where we arrange the state blocks from x1 to xt, from top to bottom, and then consider a special case in which all of these map component functions from s1 to s4 are linear, then we can actually optimize the map in closed form, we can evaluate its inverse in closed form, and we actually obtain a very familiar equation after a bit of reformulation, which you might recognize as your ensemble Kalman smoother. If, on the other hand, we choose the exact opposite ordering, arranging the states backwards in time, exploiting as much conditional independence as we can, a property that doesn't fit into this talk, and once more consider this linear special case, then we end up with a different set of equations corresponding to the Ensemble Transport Smoothers, which starts with an ensemble Kalman filtering update in the second map component and then propagates this update backwards along the graph over sequences of overlapping state spaces in these lower map components from S3 and S4. Now, this is already a really interesting finding. It basically shows us that by adopting the unifying perspective of an ensemble transport smoother, we can derive existing Kalman-type smoothers as linear special cases. But the really interesting thing about this, of course, is that we're not limited to looking at the linear special case. And in fact, we can make our map component functions as nonlinear as we want, and thus derive nonlinear generalizations to these algorithms. Which, if we go back to the motivating slide earlier, was one of the huge drawbacks of Kalman-type methods, their fundamental limitation to linear updates. And if we can overcome this limitation with transit methods, then we're a large step closer to implementing really interesting and powerful nonlinear smoothing algorithms. But before we go happily generalizing both types of smoothers, it actually turns out that they don't generalize equally well. For a number of reasons, backward smoothers are better suited for nonlinear generalization. The two main reasons for this are that backward smoothers turn out to be more robust to small ensemble sizes. This is because backward smoothers suffer less from spurious correlation, and this becomes really useful in nonlinear smoothing because a greater ability to fit real structure also means a greater ability to fit noise, which you want to avoid. The second advantage is that backward smoothers don't actually have to implement a smoothing update at every time step, but they can do so at irregular intervals, and in the most extreme case, even just once at the very end, which is more computationally efficient than trend analysis smoothers, which have to do this at every time step. In the following, we will not first consider backward smoothers. Now, the first example we consider is a very simple one-dimensional test case in which we assume that the true state just follows a sine curve. And to make things more interesting, we assume that we only observe the absolute value of a true state, which of course means that there's an equivalent set of positions on the negative half-plane which the system cannot distinguish. We assume that our forward model is completely ignorant to the dynamics, comprising only of identity plus noise, and that the observation model likewise only sees the absolute value of a state. We run the smoother with an ensemble size of 1000, which is a lot for a one-dimensional test case, but in this example we only care about the fundamental abilities of smoothers, in the best case, not really if any kind of investigation of efficiency. We run this example in two different settings. On the top row you will see a linear ensemble transport filter from left to right, followed by a linear ensemble backward smoother from right to left. This corresponds to an ensemble Kalman filter followed by an ensemble Rauchtung-Striebel smoother. On the bottom row you will see its nonlinear generalization. Before I start the video, let's discuss some expectations we have about these results. The first thing we can expect is that since the system cannot distinguish whether true state is in the upper or lower branch, the system should be periodically bimodal. So as soon as the true state deviates from 0, the system cannot distinguish if it's in the upper or lower branch, so the posterior should split and merge again and split and merge again over and over. And we can expect that this should be a really big problem for the linear algorithms on the top row, since if we start from a Gaussian prior and then just apply linear transformations, the only thing we will ever get back is a Gaussian posterior, which of course isn't bimodal. But let's start the video and see for ourselves. As expected, the linear ensemble transport filter on the top row inflates a lot and then snaps to one of the branches, and the linear backward smoother just flattens everything out without recovering the bimodal structure. Whereas in the bottom row, the nonlinear transport filter already recovers the bimodal structure very well, and the nonlinear backward smoother flattens everything out while retaining this important posterior structure. So these are already really promising results for a nonlinear smoother, but of course this example is a little bit contrived. It's only one-dimensional and it's extremely non-Gaussian. So we also investigated it in a more conventional data assimilation test case, Lorentz 63. Lorentz 63 is a chaotic three-dimensional system in which we assume that we observe all states, and we implement our smoothers both with L2 regularization, which avoids overfitting, and inflation, which increases its robustness in small ensemble size regimes. We then compare our results not just against the linear or the one ensemble transport smoother corresponding to the ensemble Richtung-Striebe smoother, but also against a state-of-the-art benchmark, the multiple data assimilation iterative ensemble Kalman smoother. The results look as follows. On the x-axis you see model evaluations or ensemble size. On the y-axis you see the ensemble mean root square error compared to the synthetic true state. The dashed lines are ensemble transport filters, the full lines are ensemble transport smoothers based on the filters. Of course, at significantly reduced root square error. The blue line here corresponds to the linear special case. But as we increase the nonlinearity of a transport map, first to order 2, then to order 3, and then to order 5, we see that root square errors keep improving as the transport smoother becomes more capable of exploiting non-Gaussian structure. But we also observe that there's a slight but noticeable bias variance trade-off for very small ensemble sizes, which suggests that there is a cost to increasing the complexity of the transport map, and that we need sufficient ensemble size to really capitalize on the higher degree of complexity our smoothers can offer. If we plot the results of the iterative ensemble Kalman smoothers with perturbed observations or a square root formulation, we see that both of them are actually slightly less efficient than our ensemble transport smoothers. They do eventually catch up, but at significantly higher numbers of model evaluations, since they're iterative algorithms. So these results are already really quite promising, showing that our ensemble transport smoothers can compete with state-of-the-art algorithms. This brings me to a summary of our talk. In this talk, we basically looked at ensemble transport smoothers, which use triangular transport to implement the fundamental smoothing update. We found that existing Kalman type smoothers are just linear special cases of this generic ensemble transport smoother, and if we capitalize on the ability to use nonlinear update functions, then we get more powerful performance in non-Gaussian and nonlinear systems. And this brings me to the end of the talk. If you have any kind of questions about this kind of work, don't hesitate to send me an email, and thank you for your attention.